In the vast expanse of interstellar space, a traveler bearing secrets from a distant star has emerged. 3I Atlas, the third known interstellar comet, discovered in February 2023 by Brazilian amateur astronomer Leonardo Amaral, and designated C2023-A3. Its trajectory and speed of over 130,000 miles per hour confirm it originates beyond our solar system. Its icy nucleus, just 1 kilometer wide, is a frozen time capsule, releasing ancient dust and gases as it nears the Sun. By late 2024, it will fade into the cosmic abyss, making every moment of study vital. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it. On X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Astronomers believe 3I Atlas was ejected from a star system hundreds or thousands of light years away, its journey lasting millions of years. This pristine sample offers a rare chance to study the interstellar void and the diversity of planetary environments. Early analysis has detected water vapor, carbon dioxide, and complex organic molecules, the building blocks of life, in the gases released by the comet. The comet's rapid movement has driven astronomers to gather data using major telescopes like Gemini, the European Southern Observatory, NASA's Hubble, and the James Webb Space Telescope. Detailed images and tracking of changes in brightness and tail orientation could reshape our understanding of comet formation and the distribution of organic materials in the universe. 3EE, Atlas's icy core, rich in elements like carbon and oxygen, supports the theory that comets delivered life's precursors to Earth. Its trajectory and velocity offer insights into the dynamics of interstellar space, hinting at processes that eject objects into the void. As it fades, astronomers wonder how many other interstellar travelers pass through our solar system undetected. Future missions may study these visitors in greater detail, even intercepting them. For now, 3 Atlas remains a reminder of the vast mysteries beyond our solar system, inspiring new research and technological innovations. Part 1. The Visitor. On a quiet night in July 2025, astronomers at the Atlas Survey Telescope in Chile detected something unusual, a faint object moving at an impossible speed. The telescope, perched atop the Cerro Pachón Ridge in the arid Chilean landscape, was designed to scan the sky for near-Earth asteroids, but this object was unlike anything they had seen before. The Atlas telescope, with its 0.5-meter primary mirror and wide field of view, was ideally suited for detecting fast-moving objects, and it did not disappoint. Within hours of the initial sighting, follow-up observations confirmed that the object was moving at an astonishing velocity, too fast to be gravitationally bound to the Sun. Its trajectory was hyperbolic, a path that could only belong to an interstellar traveler, moving at a staggering 30 kilometers per second relative to the Sun. This was no ordinary asteroid or comet. It was a visitor from another star system. The news spread quickly through the global astronomical community, igniting a flurry of activity. Observatories on every continent trained their instruments on the incoming object, each seeking to capture data that could unravel its mysteries. The Pan-STARRS telescopes in Hawaii, which had discovered Oumuamua in 2017, provided critical early measurements of the object's trajectory, while the Large Binocular Telescope in Arizona delivered high-resolution images that hinted at its shape and composition. In Europe, the European Southern Observatory's Very Large Telescope, VLT, in Chile's Atacama Desert, deployed its advanced spectrographs to analyze the object's chemical makeup. Meanwhile, the Gemini Observatory, also in Chile, used its adaptive optics to correct for atmospheric distortion, producing some of the sharpest images of the visitor. Within days, the object was officially named 3E Atlas, a nod to its discovery by the Atlas Survey, and its status as the third known interstellar object, following Oumuamua and Borisov. But unlike its predecessors, 3I Atlas was detected early in its journey through the solar system, giving scientists a precious window to study it in detail as it approached. Oumuamua had been discovered on its way out of the solar system, its closest approach to Earth already behind it. Borisov, while observed for a longer period, had not been detected until it was relatively close to the Sun. 3I Atlas, however, was spotted months before its perihelion, its closest approach to the Sun, allowing astronomers to track its behavior as it warmed and became active. The race was on. Telescopes on Earth and in orbit turned their gaze toward this cosmic wanderer, capturing its every move. The James Webb Space Telescope, JWST, with its gold-plated mirrors and infrared sensitivity, observed the comet as it began to awaken, its surface warmed by the sun's rays. Launched in 2021, JWST was designed to peer into the distant universe, studying the first galaxies and the birth of stars. But its unique capabilities also made it ideal for studying objects closer to home, like 3I Atlas. As the comet approached the Sun, JWST's near-infrared spectrograph, NIR spec, detected the faint glow of water vapor and carbon dioxide escaping from its nucleus, providing the first clues about its composition. The Hubble Space Telescope, a workhorse of astronomy since its launch in 1990, also played a crucial role. Its Wide-Field Camera 3 captured stunning images of 3I Atlas as it developed a coma, a halo of dust and gas, that expanded to over 80,000 kilometers in diameter, larger than the planet Jupiter. Hubble's observations revealed intricate details in the comet's tail, which stretched over 1 million kilometers into space, a glittering stream of ice and dust illuminated by the sun. The tail's structure changed over time, sculpted by the solar wind and the comet's own rotation, providing insights into the physical processes at work. ESA's Mars Express and ExoMars missions provided additional perspectives from Mars orbit. The Mars Express orbiter, equipped with the Visual and Infrared Mineralogical Mapping Spectrometer, OMEGA, observed 3I Atlas as it passed through the inner solar system, its infrared eyes detecting the thermal signature of the comet's nucleus. Meanwhile, the ExoMars Trace Gas Orbiter used its nadir and occultation for Mars Discovery NOMAD instrument to study the comet's atmosphere, searching for traces of organic molecules that might hint at its origins. Even amateur astronomers joined the effort. Across the globe, backyard observers trained their telescopes on 3I Atlas, capturing its subtle cyan glow as it streaked across the night sky. Social media platforms like Twitter and Instagram were flooded with images and videos of the comet, shared by enthusiasts who marveled at the opportunity to witness an interstellar object with their own eyes. In Japan, a group of schoolchildren used a small telescope to track the comet's motion, submitting their data to professional astronomers and contributing to the global effort. For many, it was a once-in-a-lifetime opportunity to participate in a historic moment of scientific discovery. But why does 3I Atlas matter? Because it carries material shaped by another star, a chemical fingerprint of a distant planetary nursery. By studying its composition, scientists hope to unlock clues about how worlds form across the galaxy. The process of planet formation is complex and poorly understood, shaped by the interplay of gravity, chemistry, and time. In our own solar system, the building blocks of planets, dust, ice, and gas, came together over millions of years to form the worlds we see today. But how does this process differ in other star systems? Are the ingredients of planets universal, or do they vary from one system to the next? 3I Atlas offered a unique opportunity to explore these questions. Spectroscopic analysis of the comet revealed the presence of water ice, a key ingredient for life as we know it. Carbon-rich compounds, including complex organic molecules like polycyclic aromatic hydrocarbons, PAH, were also found, hinting at the potential for prebiotic chemistry, the precursor to life. Traces of metals like iron and nickel indicated that the comet formed in a system enriched by the explosions of massive stars, which produce heavy elements through nuclear fusion. These elements are essential for the formation of rocky planets, suggesting that 3E Atlas's birthplace might have been conducive to the emergence of Earth-like worlds. The ratio of heavy to light isotopes in a sample can reveal details about its origin and history. For example, the ratio of deuterium, a heavy isotope of hydrogen, to hydrogen in 3E Atlas was slightly higher than in comets from our solar system, suggesting that it formed in a colder environment where more deuterium could be incorporated into ice. This hinted at a birthplace in the outer reaches of a distant star system, where temperatures are low enough for heavy isotopes to accumulate. The European Southern Observatory's Extremely Large Telescope, ELT, still under construction in 2025, made early observations of 3I Atlas, testing its capabilities to study faint, fast-moving objects. Its advanced adaptive optics system corrects for atmospheric distortion, allowing it to resolve details that would be impossible to see with smaller telescopes. The ELT's observations of 3I Atlas revealed a nucleus just under 1 kilometer in diameter, its surface pockmarked with craters and covered in a thin layer of dust. The nucleus rotated once every 7.3 hours, a remarkably slow spin compared to many comets in our solar system, which often rotate much faster. Observation: 3E Atlas displayed remarkable similarities to comets in our own solar system, yet its origins remained unmistakably alien. Its orbit, traced back through simulations, suggested it had been wandering the galaxy for millions of years before its chance encounter with our solar system. The results indicated that 3E Atlas likely originated in the outer reaches of a distant star system, ejected by the gravitational influence of a migrating gas giant planet. This process, known as planetary scattering, is thought to be a common mechanism for the ejection of comets and other small bodies from their home systems. Interpretation: the study of 3E Atlas offered a rare opportunity to compare our solar system with others. Its composition challenged existing theories about planet formation, suggesting that the building blocks of worlds might be more universal than previously thought. The presence of water ice and complex organic molecules on an interstellar object also raised intriguing questions about the potential for life's ingredients to be widespread across the cosmos. If the conditions for habitability exist in other star systems, could life itself be more common than we imagine? The discovery of 3E Atlas fueled speculation about the potential for extraterrestrial life, inspiring new research into the chemistry and physics of planetary formation. Speculation. Some scientists wondered if 3I Atlas might not be a natural object at all. Its unusual shape, reminiscent of Oumuamua's cigar-like form, and its unexpected brightness fluctuations led a few to propose it could be an artificial construct, a relic of an advanced civilization. Harvard astrophysicist Avi Loeb, who had previously suggested that Oumuamua might be an artificial object, was among those who raised the possibility. Loeb argued that the comet's behavior, including its slow rotation and the presence of metals in its composition, was consistent with an artificial origin. However, most researchers dismissed this idea, arguing that the comet's behavior was consistent with natural processes. The lack of any detectable radio signals or other signs of technology further supported the natural origin hypothesis. As 3E Atlas reached its closest approach to Earth, just 0.25 astronomical units away, it became a fleeting target for radar observations. The Goldstone Deep Space Communications Complex in California, part of NASA's Deep Space Network, bounced radio waves off the comet, revealing a nucleus with a complex, irregular shape. The radar data suggested that the comet had likely broken apart and reassembled during its long journey through the galaxy, its structure shaped by countless collisions and gravitational interactions. The Breakthrough Listen initiative, funded by the late Stephen Hawking and Yuri Milner, used the Green Bank telescope in West Virginia to search for any signs of artificial radio signals emanating from the comet. None were found, further supporting the natural origin hypothesis. The comet's departure was as spectacular as its arrival. As it receded from the sun, its tail of dust and gas stretched out behind it like a cosmic farewell, visible in telescopes for weeks after its closest approach. Astronomers estimated that 3I Atlas would continue to emit detectable light for years as it journeyed back into interstellar space. Its trajectory would take it toward the constellation Pegasus, where it would fade into the background of stars, never to be seen again by human eyes. But its legacy would live on in the data it left behind, a treasure trove of information that would inspire generations of scientists. The data collected during 3 Atlas's brief visit has already inspired hundreds of scientific papers, each offering new insights into the mysteries of planetary formation, interstellar chemistry, and the nature of the galaxy itself. Researchers at the University of Bern in Switzerland used the comet's isotopic ratios to refine models of star formation, while a team at the University of Arizona studied its organic compounds to explore the potential for prebiotic chemistry in other star systems. At the Max Planck Institute for Astronomy in Germany, scientists analyzed the comet's trajectory to better understand the dynamics of interstellar objects, while astronomers at the University of Hawaii used its light curve to study the physical processes at work on its surface. Future missions, like NASA's proposed Interstellar probe, aim to build on these discoveries by studying more interstellar objects as they pass through our solar system. The Interstellar probe, if funded, would be the fastest human-made object ever launched, capable of reaching speeds of up to 90 kilometers per second. Equipped with advanced instruments, it would be able to study interstellar objects in unprecedented detail, providing insights into their composition, structure, and origins. Other proposed missions, such as the European Space Agency's Comet Interceptor, would use a combination of spacecraft to intercept and study interstellar objects as they pass through the solar system, providing a more detailed look at these enigmatic visitors. And for a brief moment in 2025, 3 Atlas reminded us that we are not alone in the cosmos, that the stars hold countless worlds waiting to be discovered, each with its own story to tell. The discovery of 3 Atlas inspired a new generation of astronomers, eager to explore the mysteries of the universe and uncover the secrets of distant worlds. It also fueled public interest in astronomy, as people around the globe marveled at the sight of an interstellar object streaking across the night sky. For many, it was a reminder of the vastness of the cosmos and the endless possibilities it holds, a universe filled with wonders waiting to be explored. Part 2. The Chemistry of Creation. What is 3 Atlas made of? The answer lies in its chemistry, a story written billions of years ago in the cold outer reaches of another star's protoplanetary disk. Observations from JWST revealed the presence of methanol and hydrogen cyanide, molecules that form under frigid conditions. These are not just random chemicals, they are essential building blocks for complex organic chemistry, the same processes that may have given rise to life on Earth. Methanol, for instance, is a simple alcohol that can combine with other molecules to form amino acids, the foundational compounds of proteins. Hydrogen cyanide, despite its toxicity, is a key precursor to adenine, one of the nucleobases in DNA. The presence of these compounds suggests that 3 Atlas formed in an environment rich in organic precursors, a cosmic kitchen where the ingredients for life were abundant. The comet's composition is not just a curiosity, it is a window into the early universe. The protoplanetary disk where 3 Atlas was born would have been a chaotic place, filled with swirling dust, gas, and intense radiation from the young star. Over time, the disk cooled, allowing complex molecules to form and freeze onto dust grains. These grains, coated in icy layers of water, methane, and other volatiles, eventually clumped together to form the comet we see today. The process was slow and delicate, taking millions of years, but it laid the groundwork for the rich chemistry we now observe. The protoplanetary disk, a sprawling structure that could stretch up to 100 astronomical units, ADIU, from the central star, would have been a dynamic environment. Closer to the star, temperatures could exceed 1500 Kelvin, vaporizing most materials, while in the outer reaches, temperatures could drop to as low as 30 Kelvin, allowing complex ices to form. This temperature gradient created distinct zones where different types of molecules could condense, leading to a diverse chemical inventory in the comet. But there's more. The comet's early activation, as it approached the Sun, suggests it contains highly volatile ices that sublimate at lower temperatures than most solar system comets. This points to an origin in a distant, icy region around its parent star, similar to our own Oort cloud. The Oort cloud, a spherical shell of icy bodies orbiting at the edge of the solar system, is believed to be the source of long-period comets like Hale-Bopp and Hyakutake. If 3 Atlas formed in a similar region, it could have spent billions of years in deep freeze, preserving the primordial materials from its birth. The Oort cloud is estimated to contain trillions of comets, each a frozen time capsule from the early solar system. 3. Atlas, with its unique chemistry, may offer insights into the conditions of these distant, icy reservoirs. The dust surrounding 3 Atlas also tells a story. Reflectivity patterns observed by Hubble and ground-based telescopes differ from those of typical solar system comets, hinting at variations in grain size, mineral composition, or surface coatings shaped by interstellar radiation. The dust grains, tiny specks of silicate and carbonaceous material, are like fingerprints of the comet's history. Some grains may have formed in the inner regions of the protoplanetary disk, where temperatures were high enough to vaporize rocky material. Others may have condensed in the outer reaches where ices dominate. The diversity of grain sizes and compositions suggests that 3 Atlas is a cosmic time capsule, carrying material from multiple regions of its natal disk. For example, silicate grains rich in olivine and pyroxene likely formed close to the star, while carbonaceous grains coated in ices may have originated farther out. These grains, when analyzed through spectroscopy, reveal distinct absorption features that allow scientists to infer their origins. Every molecule, every grain of dust is a clue to the comet's origins, but the picture is far from complete. As 3 Atlas continues its journey, scientists are racing to unravel its secrets before it disappears forever. The comet's trajectory will take it through the inner solar system, where solar radiation and heat will strip away its outer layers, revealing deeper, more ancient material. This process, known as outgassing, will release trapped gases and dust, creating a temporary atmosphere around the comet. For example, the detection of deuterium-enriched water could indicate that the comet formed in a cold outer region of its protoplanetary disk, as deuterium fractionation is more pronounced at lower temperatures. The clock is ticking. 3 Atlas is moving at a staggering speed of over 100,000 kilometers per hour, and its closest approach to the Sun will occur in just a few months. During this time, the comet will be subjected to temperatures exceeding 200 degrees Celsius, causing its ices to sublimate rapidly. The resulting outbursts of gas and dust will create a spectacular tail, visible even to amateur astronomers with modest telescopes. But this display comes at a cost. The intense heat and radiation will also alter the comet's surface chemistry, destroying some of the delicate organic molecules that scientists hope to study. As the comet approaches perihelion, its tail could stretch millions of kilometers, glowing faintly under the Sun's intense light. This ephemeral display will be a fleeting masterpiece, a testament to the dramatic forces at play in the solar system. One of the most intriguing questions is whether 3 Atlas could harbor prebiotic chemistry, the chemical reactions that precede the formation of life. Laboratory experiments have shown that simple organic molecules, like those found in the comet, can combine under the right conditions to form more complex compounds, such as amino acids and nucleotides. In 1953, the Miller-Urey experiment demonstrated that a mixture of gases thought to resemble the early Earth's atmosphere when exposed to electrical sparks could produce a variety of organic compounds. If similar conditions existed in the protoplanetary disk where 3A Atlas formed, it is possible that the comet carries the precursors of life, or perhaps even more advanced chemistry. For instance, the presence of glycine, the simplest amino acid, has been detected in samples from comet Wild 2, suggesting that such building blocks may be common in cometary material. Observation: the comet's tail, stretching millions of kilometers into space, is a dynamic laboratory where chemistry unfolds in real time. As the comet approaches the Sun, ultraviolet radiation breaks apart molecules, creating ions and radicals that react with other compounds in the tail. This process, known as photolysis, can produce new molecules that were not present in the original comet material. For example, water vapor in the tail can be split into hydroxyl radicals, OH, and hydrogen atoms, which then react with other molecules to form compounds like formaldehyde and carbon monoxide. These reactions offer a glimpse into the chemistry of the early solar system, when similar processes may have occurred on a much larger scale. The tail's chemistry evolves constantly, with molecules forming and dissociating in response to solar radiation and the comet's changing position. Interpretation: the chemistry of 3 Atlas is not just a record of its past, it is also a snapshot of the present. The comet's interaction with the Sun and the interstellar medium is an ongoing experiment, one that reveals how cosmic forces shape matter over time. By studying the comet's tail, scientists can learn about the effects of radiation, temperature, and pressure on complex organic molecules. This knowledge could have implications for astrobiology, the study of life beyond Earth. If life exists elsewhere in the universe, it may have arisen from similar chemical processes, driven by the same cosmic forces that shaped 3 Atlas. For example, the detection of complex organic molecules in the comet's tail could suggest that the building blocks of life are ubiquitous in the cosmos, waiting for the right conditions to assemble into living systems. Speculation: could 3I Atlas hold the key to understanding the origins of life? The comet's rich chemistry, combined with its ancient origins, makes it a tantalizing target for study. If scientists can identify prebiotic molecules or even more complex compounds in the comet's tail, it would suggest that the building blocks of life are not rare but rather common in the universe. This idea, known as panspermia, proposes that life on Earth may have originated from organic compounds delivered by comets and asteroids. While 3 Atlas is unlikely to contain life itself, its chemistry could provide evidence for the processes that led to life's emergence. For instance, the discovery of nucleobases like adenine or guanine in the comet's material would strengthen the hypothesis that the precursors of life are widespread in the cosmos, waiting for the right conditions to spark biological evolution. The journey of 3 Atlas is a fleeting opportunity, a cosmic visitor passing through our solar system on its way to the unknown. As it approaches the Sun, it will reveal its secrets, one molecule at a time. Scientists around the world are preparing for this moment, using every tool at their disposal to unlock the comet's mysteries. Telescopes on the ground and in space will track its progress, while spacecraft like the Parker Solar Probe and Solar Orbiter will study its interaction with the solar wind. The data collected during this brief encounter will shape our understanding of the universe for generations to come. For example, the solar orbiter's high-resolution imaging could capture the comet's tail in unprecedented detail, revealing the structure and dynamics of its outgassing. Meanwhile, the Parker Solar Probe's in situ measurements could provide insights into how the solar wind interacts with the comet's material, influencing its chemistry and trajectory. In the quiet corners of observatories and laboratories, researchers will pore over the data, piecing together the story of 3E Atlas. They will analyze spectra, model chemical reactions, and debate the implications of their findings. The comet's chemistry will become a textbook case, a benchmark for understanding the processes that shaped our solar system and perhaps others like it. And as the comet fades from view, its legacy will endure, a testament to the power of science to illuminate the cosmos and our place within it. Future missions inspired by 3E Atlas could target other interstellar visitors, building a more comprehensive understanding of the chemistry and dynamics of comets from beyond our solar system. Each new encounter will add to the mosaic of knowledge, revealing the universal processes that connect us to the stars. Part 3. The Solar Wind Encounter. As 3E Atlas approached the Sun, it entered a violent and dynamic environment, the solar wind. This relentless stream of charged particles, primarily electrons and protons, is ejected from the Sun's corona at speeds exceeding 400 kilometers per second, creating a turbulent sea of plasma that engulfs the inner solar system. The solar wind is not uniform. It varies in density and speed, with fast streams reaching up to 800 kilometers per second and slower streams meandering at around 300 kilometers per second. These variations create complex patterns of interaction, with faster streams overtaking slower ones and generating shock waves that ripple through the solar system. The temperature of the solar wind can reach over 1,000,000 degrees Celsius, a scorching inferno that contrasts sharply with the cold vacuum of space. As the comet plunged into this maelstrom, its fragile coma, the tenuous atmosphere of gas and dust surrounding its nucleus, was bombarded by the solar wind's relentless onslaught. The collision of these forces generated a halo of X-ray emission, a phenomenon first observed in comets in the late 1990s, but never before studied at such close proximity to the Sun. Instruments from NASA and ESA, including the Solar Wind Analyzer, SWA, and the X-ray Imaging Spectrometer, XIS, detected this glowing region with unprecedented clarity. Its shape and intensity were subtly different from typical solar system comets, hinting at unique properties of 3E Atlas that could redefine our understanding of cometary processes. The X-ray halo extended over 100,000 kilometers from the comet's nucleus, shimmering like a cosmic aurora against the blackness of space. Its luminosity varied with the intensity of the solar wind, pulsating with a rhythm dictated by the Sun's ever-changing activity. The interaction between the comet and the solar wind is not just a spectacle, it's a natural experiment unfolding in real time. By observing how the comet's coma and tail evolve in response to solar wind interactions, researchers can infer the properties of its nucleus and the distribution of volatile ices within it. For instance, the rate at which the coma's gas is ionized by the solar wind can reveal the abundance of elements like oxygen, carbon, and nitrogen, which are critical to understanding the comet's origins. Similarly, the way the comet's tail bends and twists under the influence of the solar wind's magnetic field can provide clues about the internal structure of the nucleus, including whether it is porous, fractured, or layered. These insights could help answer fundamental questions about how comets form and behave, both within our solar system and beyond. The tail of 3E Atlas stretched over 5 million kilometers, a glowing river of gas and dust that shifted and contorted as the solar wind's magnetic fields tugged at its edges. The tail's composition was a mix of ancient materials, including water vapor, carbon dioxide, and traces of organic compounds, each one a clue to the comet's origins. But the solar wind is not a constant force. It fluctuates dramatically in response to solar activity, with eruptions known as coronal mass ejections, CMEs, sending billions of tons of plasma hurtling into space at speeds up to 3,000 kilometers per second. These eruptions are often accompanied by solar flares, intense bursts of radiation that can temporarily increase the solar wind's density and velocity. During 3I Atlas's encounter, the Sun was nearing the peak of its 11-year solar cycle, a period of heightened activity that produced multiple CMEs. One such event, detected on October 12, 2031, struck the comet with a wave of plasma and magnetic energy, temporarily compressing its coma and causing its tail to brighten by over 50%. This event, captured in stunning detail by the onboard cameras, provided a rare opportunity to study how comets respond to extreme solar conditions. The CME's impact was so intense that it briefly disrupted the comet's outgassing, creating a temporary halo of ejected material that glowed brightly in ultraviolet light. The ultraviolet spectrum revealed the presence of hydroxyl ions, OH, and atomic hydrogen, both of which are products of water molecules being broken apart by the solar wind. The consequences of these interactions are not limited to the comet itself. As the solar wind strips away layers of the coma, it carries with it particles and molecules that have been locked within the comet for billions of years. These ejected materials, known as pickup ions, become part of the solar wind's flow, spreading throughout the inner solar system. By analyzing the composition of these pickup ions, researchers can trace the chemical fingerprints of 3I Atlas across vast distances, potentially linking it to other comets or even to the early solar system's primordial disk. This process, known as cometary seeding, has been theorized to play a role in the distribution of water and organic compounds across the solar system, including on Earth. The pickup ions from 3I Atlas included isotopes of hydrogen, helium, and carbon, each one a breadcrumb leading back to the comet's birthplace in the frigid outer reaches of the solar system. The isotopic ratios, particularly the abundance of deuterium relative to hydrogen, suggested that the comet formed in an environment colder than the inner solar system, further supporting the idea that it originated beyond the orbit of Neptune. However, time is running out. As 3I Atlas moves farther from the Sun, its interaction with the solar wind will diminish, and these fleeting clues will fade away. Already, the comet's tail has begun to thin, its once brilliant glow dimming as the solar wind's influence wanes. By the time the comet reaches the orbit of Venus, its coma will have shrunk to a fraction of its current size, and the X-ray halo will have disappeared entirely. For the scientists studying 3I Atlas, the next few weeks are critical. They must gather as much data as possible before the comet's secrets are lost to the void of space. The team operates in shifts, with researchers in Europe, North America, and Asia collaborating around the clock to analyze the incoming data. Every 12 hours, a new batch of images and spectra is transmitted from the spacecraft, each one revealing a new piece of the comet's story. The data is so voluminous that supercomputers are required to process it, sifting through terabytes of information to identify patterns and anomalies. Observation. The solar wind's intensity during the encounter was higher than anticipated, with particle densities reaching up to 500 per cubic centimeter, nearly double the average for this region of space. This unexpectedly strong wind may have accelerated the erosion of the comet's coma, potentially shortening the window for observations. The solar wind's pressure was so intense that it created visible shockwaves in the coma, rippling like waves on a cosmic shore. These shockwaves were detected as fluctuations in the magnetic field and plasma density, providing a direct measurement of the solar wind's impact on the comet. The shockwaves also caused the comet's tail to oscillate, creating a mesmerizing display of light and motion. Interpretation. The comet's response to the solar wind suggests that its nucleus is more porous than previously thought. This porosity could explain the rapid outgassing observed during the encounter, as well as the unusual brightness of its tail. The porous structure of the nucleus allows gases to escape more easily, creating a denser coma and a more luminous tail. This is further supported by the detection of jets of gas erupting from specific regions of the nucleus, each one a geyser of ancient material spewing into space. These jets were particularly active during periods of intense solar wind activity, suggesting that the solar wind's pressure helped to drive the outgassing process. The jets also revealed the presence of complex organic molecules, including methane, CH4, and formaldehyde, H2CO, which are thought to be precursors to life. Speculation. If the comet's nucleus is indeed highly porous, it may indicate that 3 Atlas formed in the outer reaches of the solar system, where temperatures were cold enough to preserve volatile ices in a loosely packed structure. This could make it a rare example of a pristine, unaltered comet, offering a direct link to the conditions of the early solar system. The comet's trajectory suggests it originated beyond the orbit of Neptune, in the icy depths of the Kuiper Belt, where the building blocks of the solar system remain largely untouched by time. Its porous structure may also explain its low density, which is estimated to be less than half that of water ice. This low density suggests that the comet is a fragile aggregate of ice and dust, held together by weak gravitational forces. If this is the case, 3 Atlas may be a time capsule from the dawn of the solar system, preserving the primordial materials that gave rise to planets, moons, and even life itself. As the days pass, the urgency grows. The team monitoring 3I Atlas works around the clock, poring over data from the spacecraft's instruments and coordinating with ground-based observatories to capture every possible detail. Each image, each spectrum, each measurement is a piece of a cosmic puzzle, one that may never be fully solved. But for now, the comet continues its journey, a silent traveler through the solar wind, carrying with it the story of its origins, a story written in ice, dust, and time. The comet's surface is pockmarked with craters and fractures, each one a testament to its long and tumultuous journey through the solar system. As it recedes from the sun, its tail fades like a dying ember, a final farewell before it disappears into the cold expanse of space. Yet, even as it fades, 3 Atlas leaves behind a legacy of knowledge, a trail of data that will inspire and inform future generations of scientists. Its encounter with the solar wind has revealed not just the secrets of a single comet, but the story of the solar system itself, a story of creation, chaos, and the endless dance of cosmic forces. Part 4. The Terrestrial Perspective. While space-based telescopes provided unprecedented detail about 3 Atlas, some of the most striking images came from Earth. In Egypt's Black Desert, photographer Osama Fathi captured the comet rising above dark volcanic formations and isolated acacia trees. Using long exposure techniques, he revealed the comet's delicate coma and soft cyan glow, a stark contrast to the barren landscape below. His image offered a terrestrial perspective that complemented the data from space, reminding us that even the most advanced telescopes are only part of the story. The photograph, which required Fathi to camp overnight in the harsh desert environment, became an iconic representation of the comet's journey through the inner solar system. It was featured on the covers of scientific journals and art magazines alike, bridging the gap between scientific inquiry and aesthetic appreciation. Fathi's work was not just a single image. It spawned a series of time-lapse sequences that captured the comet's motion against the backdrop of ancient geological features, emphasizing the fleeting nature of celestial events against the permanence of Earth's landscape. These images inspired other photographers to embark on similar expeditions, creating a global movement to document the comet from unique terrestrial vantage points. One such photographer, Maria Elena Rodriguez, traveled to the Atacama Desert in Chile, one of the driest places on Earth, to capture 3E Atlas against the backdrop of the desert's otherworldly landscape. Her images revealed the comet's tail stretching across the sky, its wispy tendrils intertwining with the faint glow of the Milky Way. Rodriguez's work highlighted the delicate interplay between the comet and the natural environment, as the arid, high-altitude conditions of the Atacama provided an unobstructed view of the night sky. Her photographs were exhibited in galleries across South America, drawing attention to the importance of preserving dark sky locations for both scientific research and cultural heritage. Meanwhile, in the frigid landscapes of Iceland, photographer Björn Jonsson braved sub-zero temperatures to capture the comet reflecting off the surface of glacial lakes. His images showcased the comet's ethereal beauty in stark contrast to the icy terrain, creating a visual narrative that blended the celestial with the terrestrial. Amateur astronomers around the world played a crucial role in monitoring 3E Atlas. Their observations, often made with small telescopes, provided continuous coverage across different time zones and sky conditions. These citizen scientists were the first to notice key events such as outbursts or tail disconnection, which could reveal internal layering or fragmentation within the comet. For example, on March 15, 2031, a retired engineer in Australia detected a sudden brightening of the comet's nucleus, which was later confirmed by professional observatories to be a major outburst caused by the release of trapped volatile gases. This event led to a cascade of follow-up studies, as scientists rushed to analyze the composition of the ejected material. The outburst was so significant that it temporarily altered the comet's tail structure, creating a spectacular display that was visible even to the naked eye in dark sky locations. Amateur astronomers in Chile and South Africa were among the first to capture high-resolution images of the altered tail, which showed intricate filaments of dust and gas spreading outward like a cosmic fan. The contributions of amateur astronomers highlight the growing importance of collaboration between professional and amateur astronomers in the study of rare celestial objects. In Japan, a network of over 500 amateur observers coordinated efforts to track 3E Atlas as it passed through the constellation of Orion. Their meticulous records of the comet's tail structure and brightness fluctuations were compiled into a dataset that professional researchers used to refine models of cometary behavior. In the United States, the American Association of Variable Star Observers, AAVSO, organized a campaign to monitor the comet's light curve, resulting in over 10,000 individual measurements submitted by volunteers. These observations were critical in identifying periodic variations in the comet's activity, which may have been linked to its rotation or internal dynamics. The dataset was so comprehensive that it allowed researchers to predict future outbursts with unprecedented accuracy, providing valuable insights into the comet's internal processes. In Europe, amateur astronomers in countries like Germany, France, and Italy formed a consortium to share data and coordinate observations. Their efforts led to the discovery of subtle changes in the comet's coma, which were later attributed to the sublimation of different ices within the nucleus. These findings were published in a series of peer-reviewed papers, further cementing the role of amateur astronomers in advancing our understanding of cometary physics. In India, a group of university students set up a makeshift observatory in the Himalayas, using low-cost equipment to capture detailed images of the comet's tail. Their work was featured in a national science magazine, inspiring other young people to take up astronomy as a hobby or career. The global fascination with 3I Atlas extended beyond scientific circles. In cities like Paris and New York, public star parties were held in parks and on rooftops, drawing thousands of people who gathered to catch a glimpse of the comet through telescopes provided by local astronomy clubs. In Mumbai, a group of schoolchildren worked with their teachers to build simple telescopes from cardboard and lenses, using them to observe the comet and document its changing appearance over several nights. Their efforts were featured in a local documentary that highlighted the intersection of science and community engagement. In Rio de Janeiro, a street artist named Maria Silva created a massive mural depicting 3 Atlas soaring over the city's skyline, blending the comet's celestial beauty with the vibrant colors of Brazilian culture. The mural became a symbol of the city's connection to the cosmos and a popular gathering spot for stargazers. In Tokyo, a digital art installation projected real-time images of the comet onto the facade of a skyscraper, allowing passers-by to witness its journey in stunning detail. The installation, titled Cosmic Echo, was accompanied by an original soundtrack composed to evoke the mystery and wonder of space. It became a cultural phenomenon, drawing visitors from around the world and sparking conversations about the intersection of art and science. Meanwhile, in rural communities across Africa, mobile planetariums traveled from village to village, providing educational programs about the comet and the night sky. These initiatives reached thousands of people who might not otherwise have access to astronomical resources, fostering a sense of curiosity and connection to the cosmos. As 3 Atlas fades from view, the legacy of these observations will endure, inspiring future generations to look up and wonder what lies beyond our solar system. The comet's visit left an indelible mark on human culture, sparking a renewed interest in astronomy and space exploration. In classrooms around the world, students studied the comet's trajectory and composition as part of their science curricula, while artists created paintings, sculptures, and digital artworks inspired by its ethereal beauty. The European Space Agency, ESA, even launched a competition for young engineers to design a hypothetical mission to rendezvous with the comet during its next pass through the inner solar system, encouraging innovative thinking about future space exploration. The competition received over 5,000 submissions from students in more than 40 countries, showcasing the global enthusiasm for space science. Many of the proposals included cutting-edge technologies such as solar sails, ion drives, and advanced imaging systems, reflecting the ambition and creativity of the next generation of scientists and engineers. One submission, from a team of students in Nigeria, proposed a mission concept called Comet Chaser, which involved a fleet of small cooperative spacecraft equipped with sensors and cameras. The spacecraft would surround the comet, providing a 360-degree view of its activity and allowing scientists to study its behavior from multiple angles simultaneously. The team's proposal was so innovative that it caught the attention of international space agencies, leading to collaborations and mentorship opportunities for the students. Another submission, from a group of students in Canada, envisioned a comet harvester mission that would collect samples from the comet's tail and return them to Earth for analysis. The proposal highlighted the potential for cometary material to provide insights into the early solar system and the origins of life. In addition to its scientific impact, 3I Atlas influenced popular culture in profound ways. Filmmakers incorporated the comet into their stories, creating everything from dramatic science fiction epics to whimsical animated shorts. In one particularly moving film, titled Comet's Tale, a young girl living in a remote village forms a deep connection with the comet, using its nightly appearance as a source of hope during a difficult time in her life. The film received critical acclaim and was screened at festivals worldwide, introducing the comet to audiences who might not have otherwise been exposed to its story. Meanwhile, musicians wrote songs inspired by 3 Atlas, ranging from orchestral compositions that evoked the grandeur of the cosmos to indie ballads that explored themes of transience and wonder. These cultural works ensured that the comet's legacy would live on long after it disappeared from the night sky. The terrestrial perspective of 3 Atlas also highlighted the importance of preserving dark skies. As light pollution continues to threaten our ability to observe the night sky, the comet's appearance served as a reminder of what we stand to lose. In response, many cities implemented new policies to reduce light pollution, including dimming streetlights and encouraging businesses to adopt dark sky-friendly lighting practices. These efforts were not only beneficial for astronomy, but also for wildlife and human health, as excessive artificial light has been linked to disruptions in circadian rhythms and other biological processes. The comet's visit sparked a global conversation about the value of darkness and the need to protect it for future generations. In some regions, the impact of light pollution was starkly evident. In urban areas like Los Angeles and Shanghai, the comet was barely visible due to the overwhelming glow of city lights. This stark contrast between urban and rural skies underscored the urgency of addressing light pollution. Grassroots organizations in these cities launched campaigns to raise awareness and advocate for changes in lighting policies. Their efforts were met with widespread support as people began to recognize the importance of preserving the night sky, not just for astronomy, but for the well-being of all living things. The comet's visit became a catalyst for change, inspiring communities to take action and reclaim the darkness that has been lost to urbanization. Observation. The terrestrial perspective of 3E Atlas enriched our understanding of the comet in ways that space-based observations alone could not. By combining data from professional telescopes with the ground-level insights of amateur astronomers and artists, scientists gained a more complete picture of the comet's behavior and composition. The comet's passage also underscored the importance of public engagement in science, as the contributions of amateur astronomers, photographers, and educators played a vital role in documenting and interpreting the event. Interpretation. The collaboration between amateur and professional astronomers during the passage of 3E Atlas represents a shift in how scientific research is conducted. Crowdsourced data and public engagement are increasingly seen as vital components of modern astronomy, allowing for broader participation and more comprehensive datasets. This approach not only advances scientific knowledge, but also fosters a deeper connection between the public and the cosmos. The comet's visit demonstrated that science is not just the domain of experts, but a collective endeavor that benefits from the curiosity and creativity of people from all walks of life. Speculation. As technology continues to advance, it is possible that future cometary encounters will involve even greater levels of public involvement. Imagine a world where anyone with a smartphone can contribute meaningful data to scientific research, or where virtual reality allows people to experience comets up close in real time. Such innovations could transform how we interact with the universe, making the wonders of space exploration accessible to everyone. For example, augmented reality glasses could project detailed annotations and visualizations directly onto the night sky, allowing observers to see the invisible forces and structures that shape celestial objects. This kind of immersive experience could revolutionize both scientific research and public education, bringing the cosmos closer to home than ever before. In the not-too-distant future, holographic displays could allow families to gather in their living rooms and watch a comet's journey in 3 dimensions, with real-time data streaming in from spacecraft and ground-based observatories. Schools could use these technologies to create interactive lessons, allowing students to explore the solar system and beyond in ways that were once the stuff of science fiction. The possibilities are endless, and the legacy of 3E Atlas serves as a reminder of how far we have come and how much further we can go. Part 5. The Interstellar Connection. 3E Atlas is not the first interstellar visitor, but it may be the most revealing. Its detection, along with Oumuamua in 2017 and Borisov in 2019, has challenged our understanding of how common these objects are. For centuries, astronomers believed interstellar visitors were exceedingly rare, perhaps appearing once every few hundred years. But the discovery of 3 such objects in less than a decade suggests they may be far more abundant than previously thought. Initial estimates now propose that there could be thousands of such objects passing through our solar system at any given time, most of them too small or too faint to detect with current technology. These objects, ranging from a few meters to several kilometers in size, move at astonishing velocities, often exceeding 50 kilometers per second, making their detection a fleeting opportunity. Their trajectories, hyperbolic in nature, are distinct from the elliptical orbits of objects native to our solar system, hinting at origins far beyond the influence of our Sun. The first interstellar object, Oumuamua, was a revelation. Its elongated shape, measuring roughly 200 meters in length, baffled scientists, as did its tumbling motion. It was unlike any asteroid or comet observed in our solar system, and its trajectory indicated it had been wandering through interstellar space for millions of years. Borisov, the second interstellar visitor, was more comet-like, with a visible coma and tail, but its composition hinted at a formation process distinct from comets in our own system. Analysis of Borisov's tail revealed the presence of cyanogen, a toxic gas composed of carbon and nitrogen, which is rarely found in comets from our solar system. This peculiar composition suggests Borisov formed in a system with a higher abundance of carbon-rich materials, perhaps near a carbon-rich star. 3 Atlas III has offered even more surprises. Its composition, rich in heavy metals like iron and nickel, as well as complex organics, suggests it may have formed near a supernova or in the dense chaotic environment of a protoplanetary disk. The presence of heavy metals indicates that 3 Atlas likely originated in a system where cataclysmic events such as supernovae enriched the surrounding material with these elements. Its organics, meanwhile, hint at the possibility of prebiotic chemistry, a tantalizing clue to the potential for life beyond Earth. As detection networks improve, it is likely that many more interstellar objects will be identified, each offering a unique window into the conditions of distant star systems. These visitors carry raw material from other planetary nurseries, providing a direct comparison point for understanding how worlds form throughout the galaxy. For instance, the presence of certain isotopes in 3 Atlas suggests it may have originated in a system where stellar winds were particularly intense, a condition that could influence the types of planets that form. These winds, driven by the intense radiation of young stars, can sculpt the composition and structure of protoplanetary disks, determining whether a system will give rise to rocky planets, gas giants, or something entirely different. By studying their chemistry and structure, scientists can refine models of planetary formation and explore the diversity of planetary systems across the cosmos. The European Space Agency's Gaia mission, which aims to map over 1 billion stars in the Milky Way, has already identified several candidate interstellar objects, though none have been confirmed as definitively as Oumuamua, Borisov, or 3 Atlas. As more data is collected, these candidates may provide additional insights into the origins and trajectories of interstellar visitors. But the interstellar connection goes beyond mere curiosity. These objects may hold clues to the origins of life itself. The discovery of amino acids and other prebiotic compounds in meteorites has long suggested that the building blocks of life could be widespread in the universe. If interstellar objects like 3 Atlas carry similar compounds, it would imply that the ingredients for life might be distributed across the galaxy, delivered to nascent planetary systems during their formation. This raises the tantalizing possibility that life could emerge in countless star systems, each with its own unique chemical and environmental conditions. For example, the Murchison meteorite, which fell in Australia in 1969, contained over 70 different amino acids, many of which are not found in life on Earth. If interstellar objects carry similar organic molecules, they could seed new worlds with the raw materials necessary for life to take hold. Observation. 3. Atlas exhibits a peculiar reddish hue, which scientists attribute to the prolonged exposure of its surface to cosmic radiation. This radiation, which permeates interstellar space, gradually alters the chemistry of the object, creating complex organic molecules that could be precursors to life. The reddish color is a signature of this process, a cosmic fingerprint of the object's journey through the void. Spectroscopic analysis of 3I Atlas has revealed the presence of tholins, complex organic compounds formed when simpler molecules like methane are irradiated by cosmic rays. These tholins are thought to play a critical role in the formation of prebiotic molecules such as amino acids and nucleotides, which are essential for life. Tanaroi. Interpretation. The reddish hue of 3 Atlas is not unique. Similar coloration has been observed in objects within the Kuiper Belt and Oort cloud, regions at the outer edges of our solar system. This suggests that the processes shaping interstellar objects may also occur in the farthest reaches of our own system. However, the intensity of the reddening in 3I Atlas implies a longer exposure to cosmic radiation consistent with its interstellar origin. The New Horizons spacecraft, which flew past Pluto and the Kuiper Belt object Arrokoth, detected similar reddish hues on these distant bodies, indicating that cosmic radiation plays a universal role in shaping the chemistry of objects at the edges of star systems. Chapfur. Speculation. If 3 Atlas and other interstellar objects are indeed seeding young planetary systems with organic compounds, it raises the question of whether life on Earth might have been influenced by similar events. Some theories propose that the building blocks of life were delivered to Earth by comets and asteroids during the late heavy bombardment, a period of intense impact events roughly 4 billion years ago. Could some of those objects have been interstellar in origin? The answer could redefine our understanding of life's beginnings. Recent studies of the Moon's craters suggest that during the late heavy bombardment, Earth may have been struck by as many as 22,000 impactors larger than 20 kilometers in diameter. If even a small fraction of these were interstellar objects carrying prebiotic compounds, they could have played a significant role in the emergence of life on our planet. But for now, 3 Atlas remains our best hope for unlocking these secrets. Its brief visit has already yielded a treasure trove of data, but there's still more to learn. As it continues its journey through the solar system, astronomers are racing to gather as much information as possible before it fades from view. Telescopes around the world are trained on its path, capturing spectral data, measuring its velocity, and mapping its trajectory with unprecedented precision. Each new observation brings us one step closer to deciphering the story of its origin and the broader tale of the cosmos. The Large Synoptic Survey Telescope, LSST, currently under construction in Chile, is expected to revolutionize the study of interstellar objects by scanning the entire sky every few nights. With its unprecedented sensitivity, the LSST could detect hundreds of interstellar visitors in the coming decades, vastly expanding our understanding of these enigmatic objects. The interstellar connection is more than just a scientific curiosity. It is a reminder of our place in the universe. Every interstellar object that passes through our solar system is a messenger from the cosmos, carrying with it the story of distant stars and the potential for life beyond our own world. As we continue to explore these visitors, we are not just studying rocks and ice, we are studying the very fabric of the universe, the threads that connect us to the stars. The Breakthrough Starshot Initiative, a research and engineering program aimed at demonstrating proof of concept for ultra-fast light-driven nanocraft, envisions sending tiny spacecraft to nearby star systems at speeds up to 20% the speed of light. If successful, such missions could one day allow us to study interstellar objects in their native environments, providing an unparalleled window into the processes that shape the cosmos. For now, however, we must rely on the fleeting glimpses afforded by objects like 3 Atlas, reminders that the universe is far stranger and more wondrous than we can imagine. Part 6. The Prebiotic Puzzle. At the heart of 3I Atlas's story lies a deeper question. Could interstellar comets have played a role in the origins of life? The volatile molecules detected in the comet, such as methanol and hydrogen cyanide, are central to discussions of prebiotic chemistry. These molecules do not indicate biological processes, but they reinforce the idea that the essential building blocks for complex organic chemistry occur naturally in cold regions around stars. Astronomers have identified over 200 different molecules in interstellar space, including complex organics like polycyclic aromatic hydrocarbons, which are known to be resilient and abundant in the cosmos. The presence of these molecules in comets suggests that they could have been delivered to Earth during the late heavy bombardment, a period approximately 4 billion years ago when the inner solar system was pummeled by asteroids and comets. During this time, the Earth's surface was subjected to intense impact events, with some estimates suggesting that up to 10^23 kilograms of cometary material could have been delivered, enriching the early Earth with a vast array of organic compounds. The delivery of these organic compounds to Earth may have been a critical step in the emergence of life. Laboratory experiments have shown that when simple molecules like hydrogen cyanide and methanol are exposed to ultraviolet light or other energy sources, they can form more complex compounds, including amino acids, the building blocks of proteins. For example, the Miller-Urey experiment in 1953 demonstrated that a mixture of gases thought to resemble the early Earth's atmosphere, when subjected to electrical sparks, could produce amino acids and other organic molecules. While the exact conditions of early Earth are still debated, the experiment highlighted the potential for abiotic synthesis of life's precursors. Modern reanalyses of the Miller-Urey experiment have identified even more organic compounds, including 22 amino acids and 5 nucleic acid bases, further emphasizing the potential richness of prebiotic chemistry under early Earth conditions. Studying how these molecules are stored, released, and transformed as the comet interacts with sunlight provides insights into chemical pathways that may be common across the galaxy. Comets like 3I Atlas are essentially frozen time capsules, preserving materials from the early solar system. As they approach the sun, these icy bodies begin to sublimate, releasing gases and dust that have been locked away for billions of years. This process allows scientists to analyze the composition of comets using spectroscopy, revealing the presence of molecules like formaldehyde, ethanol, and even glycine, a simple amino acid. The Rosetta mission to Comet 67P, Churyumov-Gerasimenko, for instance, detected glycine and other organic compounds, further supporting the idea that comets could have seeded Earth with the ingredients for life. The Rosetta mission also found that the ratio of deuterium to hydrogen in the comet's water was higher than that found in Earth's oceans, suggesting that while comets may have contributed to Earth's water, they are not the sole source. If similar processes occur in other star systems, it raises the tantalizing possibility that the ingredients for life are not unique to Earth but are instead widespread throughout the universe. Astronomers have observed protoplanetary disks around young stars, which are rich in organic molecules. These disks are the birthplaces of planets, and the presence of complex organics suggests that the raw materials for life may be incorporated into forming worlds from the outset. For example, the Atacama Large Millimeter, Submillimeter Array, ALMA, has detected methanol, formaldehyde, and other prebiotic molecules in the disk surrounding the star HL Tauri, located about 450 light-years away. This finding implies that the chemical foundation for life could be a universal feature of planet formation. Recent observations by ALMA have also revealed the presence of complex organic molecules in the disk surrounding the young star MWC 480, including methyl cyanide, which is involved in the synthesis of amino acids. 3. Atlas offers a glimpse into these processes, but the full story remains elusive. The comet's trajectory and composition provide clues about its origin, but its interstellar nature raises questions about how it formed and whether it is representative of other comets in the galaxy. Some theories suggest that interstellar comets like 3E Atlas could have originated in the outer reaches of other star systems, where temperatures are low enough for complex molecules to form and accumulate. Others propose that they might have been ejected from their home systems during chaotic gravitational interactions, wandering through interstellar space for millions or billions of years before entering our solar system. The detection of Oumuamua in 2017, the first observed interstellar object, revealed a cigar-shaped body with no visible coma or tail, challenging scientists to rethink the diversity of interstellar visitors. Borisov, detected in 2019, was the first confirmed interstellar comet, exhibiting a coma and tail similar to solar system comets, but with a composition that hinted at a different origin. As the comet fades from view, the data it leaves behind will continue to fuel debates about the origins of life for years to come. The study of interstellar comets is still in its infancy, but each new discovery adds to our understanding of the cosmos and our place within it. The detection of 3E Atlas and other interstellar visitors, such as Oumuamua in 2017 and Borisov in 2019, has opened a new chapter in astrobiology. These objects challenge our assumptions about the boundaries of star systems and the exchange of material across the galaxy. By analyzing their composition and trajectories, scientists hope to unravel the mysteries of how life began and whether it might exist elsewhere in the universe. The study of interstellar comets also has implications for planetary defense, as understanding their orbits and behaviors can help predict and mitigate potential future impacts on Earth. The quest to understand the prebiotic puzzle extends beyond comets to other celestial bodies. Meteorites, fragments of asteroids and comets that survive passage through Earth's atmosphere, have also been found to contain amino acids and other organic compounds. The Murchison meteorite, which fell in Australia in 1969, contains over 70 different amino acids, many of which are not found in terrestrial biology. This suggests that the prebiotic chemistry occurring in space may be even more diverse than what is found on Earth. Additionally, the Cassini mission to Saturn's moon Enceladus detected complex organic molecules in the plumes of water vapor erupting from the moon's icy surface, hinting at the possibility of prebiotic chemistry occurring within its subsurface ocean. The search for the origins of life is not confined to our solar system. The discovery of exoplanets, planets orbiting other stars, has revolutionized our understanding of planetary systems. With over 5,000 exoplanets confirmed to date, astronomers are beginning to characterize their atmospheres using techniques like transit spectroscopy. The James Webb Space Telescope, JWST, launched in 2021, is equipped with instruments capable of detecting biosignatures, chemical indicators of life, in the atmospheres of distant worlds. The detection of molecules like oxygen, ozone, methane, and nitrous oxide in an exoplanet's atmosphere could suggest the presence of biological processes. JWST's first observations of exoplanet atmospheres have already revealed the presence of water vapor, carbon dioxide, and other molecules, paving the way for future discoveries. Observation: 3 Atlas contains molecules like methanol and hydrogen cyanide, which are key to prebiotic chemistry. 3. Interpretation: these molecules suggest that comets could have delivered the building blocks of life to Earth during the late heavy bombardment. Speculation: if similar comets are common in other star systems, the ingredients for life may be widespread throughout the galaxy. The study of interstellar comets could revolutionize our understanding of life's origins and the potential for extraterrestrial life. As we continue to explore the cosmos, the prebiotic puzzle remains one of the most profound questions in science, driving us to look deeper into the universe and closer to home for the answers that will reveal our place in the grand tapestry of existence. Part 7. The Future of Interstellar Science. What comes next for 3E Atlas? As it moves outward from the Sun, its coma and tail will continue to evolve, revealing new details about its internal structure and composition. The comet's icy nucleus, estimated to be roughly 100 meters in diameter, will gradually release trapped gases and dust as it warms, painting a dynamic portrait of its origins. JWST and Hubble may contribute additional data as long as the comet remains bright enough, their advanced optics capturing subtle shifts in its chemical signature. Ground-based telescopes, such as the Large Binocular Telescope in Arizona or the European Southern Observatory's Very Large Telescope in Chile, will track its fading light, their massive mirrors gathering photons from distances exceeding 500 million kilometers. Amateur astronomers will also play a critical role, monitoring brightness variations and structural changes that could indicate outbursts or fragmentation. Their collective observations, often coordinated through global networks like the British Astronomical Association's Comet Section, will provide a continuous record of 3E Atlas's behavior as it recedes into the cosmic void. These observations are not just passive recordings, they are active contributions to a global database that will help astronomers refine their models of cometary behavior and predict future trajectories with unprecedented accuracy. But the real value of 3E Atlas lies not just in what it reveals about itself, but in what it tells us about the universe beyond our solar system. By studying this rare visitor, scientists are refining models for interstellar comet behavior and establishing baseline expectations for future interstellar visitors. For instance, the unexpected detection of cyanogen, Cn, and diatomic carbon, C2, in 3I Atlas's spectrum has challenged existing theories about the chemical evolution of interstellar objects. These insights could help us understand how material moves through the galaxy and how planetary systems evolve over time. Observations of 3E Atlas have already suggested that interstellar comets may be more chemically diverse than previously thought, implying that the building blocks of planets and life could vary significantly across star systems. As our understanding deepens, it may reshape our ideas about habitability and the potential for extraterrestrial life. For example, the presence of complex organic molecules in 3I Atlas's tail could indicate that the raw materials for life are more ubiquitous in the universe than we once believed. This could inspire new research into astrobiology, pushing scientists to explore how life might emerge in environments far different from our own. The trajectory of 3 Atlas also offers clues about the dynamics of the interstellar medium. Its path suggests it originated from the direction of the constellation Virgo, traveling through space for millions of years before being captured by the Sun's gravity. By tracing its course, astronomers can map the gravitational influence of nearby stars and the distribution of matter in the Milky Way's local neighborhood. This data could inform future missions to study interstellar objects, such as the proposed Interstellar Probe, which aims to travel beyond the heliopause and explore the boundary between our solar system and interstellar space. Such missions, slated for launch in the late 2030s, could directly sample the material 3 Atlas has traversed, providing unprecedented insights into the composition and behavior of the interstellar medium. For instance, the Interstellar Probe could detect trace elements or isotopes in the interstellar medium that are not present in our solar system, offering clues about the origins of the material that formed our own planetary neighborhood. Additionally, the probe might encounter dust grains or molecular clouds that have interacted with 3 Atlas, revealing how interstellar objects shape and are shaped by their environments. As 3 Atlas fades into interstellar space, its legacy will endure. a testament to humanity's unending quest to understand our place in the cosmos. Its journey has inspired new questions and sparked collaborations across disciplines, from astrochemistry to astrophysics. For example, researchers at the University of Hawaii are using data from 3I Atlas to develop more accurate models of comet outgassing, while teams at NASA's Goddard Space Flight Center are studying its interactions with the solar wind to better understand how interstellar objects are sculpted by stellar environments. These efforts reflect the interconnected nature of scientific discovery, where each observation builds on the last, pushing the boundaries of what we know further into the unknown. At the same time, engineers at the Jet Propulsion Laboratory are designing new propulsion systems that could one day allow us to intercept and study interstellar comets in real time, rather than relying on fleeting observations as they pass through our solar system. These advancements could enable missions to rendezvous with interstellar objects, deploying landers or orbiters to study them up close for extended periods. Such missions would require cutting-edge technologies, such as advanced ion drives or even nuclear propulsion, to achieve the necessary speeds and maneuverability. The study of 3 Atlas has also inspired a new wave of public engagement with astronomy. Amateur astronomers around the world have shared their images and observations on social media, creating a global community of citizen scientists. Schools and universities have incorporated 3I Atlas into their curricula, using it as a case study to teach students about comets, interstellar travel, and the scientific method. This grassroots enthusiasm has even influenced policy, with governments and space agencies recognizing the importance of investing in interstellar research. For example, the European Space Agency has announced plans to fund new telescopes and missions specifically designed to detect and study interstellar objects, ensuring that future visitors like 3 Atlas will not go unnoticed. These initiatives could lead to the development of dedicated interstellar observatories, such as space-based telescopes equipped with coronagraphs to block out the glare of nearby stars and reveal faint interstellar objects. Such observatories could operate in tandem with ground-based arrays, providing continuous coverage of the sky and increasing the likelihood of detecting rare interstellar visitors. Observation. 3A. Atlas's fading light will become increasingly difficult to detect, but its influence on interstellar science will only grow stronger. As it recedes, it will join the ranks of other groundbreaking objects, such as Oumuamua and Borisov, as a cornerstone of our understanding of the universe beyond the solar system. Its unique chemical fingerprint, combined with its dynamic behavior, has already rewritten parts of our textbooks and will continue to inspire new theories and technologies. For instance, the discovery of previously unknown compounds in 3I Atlas's tail could lead to breakthroughs in materials science, as researchers explore how these substances might be used in everything from advanced electronics to spacecraft construction. The presence of rare isotopes in its composition could also inform nuclear physics, providing insights into the processes that forge these elements in distant stars. Interpretation. The study of 3 Atlas underscores the importance of serendipity in science. Its unexpected arrival in our solar system has provided a rare opportunity to examine a relic from another star system up close. By leveraging this chance encounter, scientists are not only learning about the comet itself, but also about the larger cosmic processes that shaped it. This interstellar visitor serves as a reminder that some of the most profound discoveries come from looking beyond the familiar, embracing the unknown, and being prepared to seize the moment when it arrives. For example, the unexpected detection of certain isotopes in 3I Atlas's spectrum has led to new hypotheses about the nucleosynthesis processes that occurred in its parent star system, offering insights into the life and death of stars across the galaxy. These insights could help refine models of stellar evolution and galactic chemical enrichment, painting a clearer picture of how the universe has changed over time. Chapeau de speculation. As our technology advances, it is possible that future missions could intercept interstellar objects like 3I Atlas, collecting samples or even landing on their surfaces to study them in detail. Such endeavors, while technically challenging, would revolutionize our understanding of the universe and our place within it. Imagine a robotic probe touching down on the icy nucleus of a comet that has traveled through the void for eons, analyzing its composition and sending back data that rewrites the story of our origins. This is the promise of interstellar science, a frontier where every discovery is a step closer to answering the ultimate question: are we alone in the cosmos? For example, if a future mission were to find evidence of microbial life or prebiotic chemistry on an interstellar object, it would fundamentally alter our understanding of biology and our place in the universe. Such a discovery would not only confirm that life can emerge beyond Earth, but also provide a roadmap for how it might have happened here and elsewhere. This could inspire new fields of research, such as interstellar ecology, which might explore how life adapts to the extreme conditions of space and how it could potentially migrate between star systems. Part 8. The Final Countdown. The clock is ticking. 3 Atlas, the interstellar comet that has captivated astronomers and the public alike, will soon leave the inner solar system. Its journey has been one of monumental proportions, traversing distances that are almost incomprehensible to the human mind. As it retreats, its coma, the nebulous envelope of dust and gas that has given it a ghostly glow, and its tail will dissipate into the void, leaving no visible trace of its passage. But the data it leaves behind will remain, a treasure trove of information that will fuel scientific discovery for decades to come. This data includes high-resolution spectra revealing the comet's chemical composition, detailed images capturing its morphology, precise measurements of its dust production, and X-ray profiles that offer insights into its interaction with the solar wind. Scientists have already begun to unravel the complexities of its structure, noting that its nucleus, estimated to be roughly 1.2 kilometers in diameter, is unusually dense, suggesting it may have formed under intense gravitational pressures in its distant birthplace. The scientific community is abuzz with anticipation. Researchers across the globe are already poring over the preliminary data, their minds racing with possibilities. Spectra from the comet have revealed the presence of molecules never before detected in an interstellar object, hinting at the unique chemical processes that occur in the cold, dark reaches of interstellar space. Among these are traces of deuterium-enriched compounds, isotopes of nitrogen and carbon, and even complex organic molecules that challenge our understanding of interstellar chemistry. Images of the comet's nucleus, captured with unprecedented clarity, are challenging existing models of cometary structure and behavior. These images, some taken by the Hubble Space Telescope, show pockmarked surfaces and strange angular features that suggest the comet may have undergone violent collisions or extreme temperature changes during its interstellar voyage. The measurements of dust production have provided valuable insights into the composition and dynamics of interstellar material, while X-ray profiles have shed light on the complex interactions between the comet and the solar environment. 3. Atlas will not return. Its journey through our solar system is a once-in-a-lifetime event, a fleeting opportunity to study material from another star. The comet's trajectory, carefully plotted by astronomers, shows that it will continue to accelerate as it moves away from the Sun, eventually reaching speeds that will carry it back into the interstellar medium. This journey is not a closed loop but a linear path, a one-way trip through the cosmos. Its brief encounter with our solar system, a mere blink of an eye in cosmic terms, has given us a glimpse into the mysteries of the universe beyond our own celestial neighborhood. As it departs, it will pass through the Kuiper Belt, a region of icy bodies beyond Neptune, and then the the Oort cloud, a vast spherical shell of cometary material that marks the outermost boundary of the Sun's gravitational influence. By the time it reaches the edge of the Oort cloud in approximately 2035, it will be traveling at a speed of nearly 32 kilometers per second, propelled by the cumulative gravitational influence of the solar system. But its legacy will endure, inspiring future generations to look beyond our solar system and wonder what lies in the vast expanse of interstellar space. The data collected from 3I Atlas will serve as a foundation for future research, a springboard for new theories and discoveries. It will inform the design of future missions as scientists strive to develop more advanced instruments and techniques for studying interstellar objects. The comet's visit has also sparked renewed interest in the search for extrasolar planets and the study of exoplanetary systems, as researchers seek to understand the diversity of worlds that exist beyond our own. NASA, the European Space Agency, and private enterprises like SpaceX are already exploring concepts for interstellar probes that could one day follow in 3 Atlas's footsteps, equipped with technologies like solar sails, ion drives, or even nuclear propulsion systems. These missions, though still decades away, represent humanity's first steps toward becoming an interstellar species. As the comet fades into the cosmic abyss, it leaves us with a final question. What other secrets does the universe hold, waiting to be discovered by those who dare to look? The study of 3 Atlas has shown us that the universe is full of surprises, that even the most seemingly ordinary objects can harbor extraordinary secrets. It has reminded us of the importance of curiosity and the power of exploration, of the need to push the boundaries of our knowledge and to venture into the unknown. As we bid farewell to this interstellar traveler, we are left with a sense of wonder and anticipation, eager to see what other wonders the universe has in store for us. In the coming years, astronomers will continue to monitor 3I Atlas as it retreats, using ground-based observatories and space telescopes like the James Webb Space Telescope to capture its fading light. These observations will not only provide a better understanding of the comet's composition and behavior, but also refine our models of interstellar trajectories and dynamics. Bari Tour Observation. The trajectory of 3 Atlas has been meticulously tracked using advanced telescopes and computational models. Its speed upon entering the solar system was approximately 30 kilometers per second, and it is expected to exit at a slightly higher velocity due to the gravitational slingshot effect of the Sun. This increase in speed, though minute, is a testament to the profound influence of celestial mechanics on the motion of interstellar objects. Astronomers have noted subtle perturbations in its path caused by the gravitational pull of Jupiter and Saturn, which slightly altered its course and provided a rare opportunity to study the interplay between interstellar objects and planetary systems. Interpretation. The chemical composition of 3 Atlas, as revealed by spectroscopic analysis, suggests that it originated in a region of space far removed from our own. The presence of exotic molecules and isotopes indicates that it formed under conditions vastly different from those in the solar system. This raises intriguing questions about the diversity of interstellar environments and the processes that govern the formation of comets and other small bodies. For instance, the comet's high deuterium-to-hydrogen ratio suggests it may have formed in a cold molecular cloud where such isotopes are more abundant. Similarly, the detection of heavy metals like iron and nickel in its dust suggests it may have passed through regions of intense stellar activity, where supernovae enriched the interstellar medium with such elements. Speculation. Could 3 Atlas be a harbinger of things to come? As our technological capabilities continue to advance, it is possible that we will detect and study more interstellar objects in the future. Each of these encounters will provide us with new insights into the nature of the universe and the processes that shape it. Perhaps one day we will even be able to send probes to study these objects up close, gathering data that will revolutionize our understanding of the cosmos. Future missions like the proposed Interstellar Probe concept, which aims to travel to the edges of the heliosphere and beyond, could one day intercept an interstellar object, collecting samples of its material and sending them back to Earth for detailed analysis. Such a mission would represent a monumental leap in our ability to explore the universe and uncover its deepest mysteries. The final moments of 3 Atlas's journey through the inner solar system are approaching. As it recedes into the distance, its light fading from view, it leaves behind a legacy of discovery and inspiration. The data it has provided will continue to be analyzed and interpreted, revealing new insights and challenging our understanding of the universe. And as we look to the future, we are filled with a sense of excitement and anticipation, eager to see what other wonders await us in the vast, unexplored reaches of interstellar space. Astronomers are already developing new techniques to detect and track interstellar objects, using advanced algorithms and machine learning to sift through the immense volumes of data collected by modern telescopes. These efforts, combined with the growing public interest in interstellar exploration, ensure that 3 Atlas will not be the last visitor from beyond the stars. Instead, it will be remembered as the herald of a new era of discovery, one that promises to transform our understanding of the cosmos and our place within it.